This conference will now be recorded.
Okay, I think we'll go ahead and get started. I know we still have a few people joining, but we will go ahead and get started. Welcome everyone. My name is Jessica Enix and I'm with the ACIL staff, and I would like to welcome you to today's presentation. ACIL is proud to offer this educational webinar thanks to the support of our longtime sponsors, Waters. While this webinar is educational, it would be amiss if we did not recognize the support that Waters has offered ACIL, and we appreciate their support. Before we begin our presentation, I'd like to review a few points of protocol so that you'll get the most out of your webinar experience. Remember, you are listening to the webinar via a conference service. If you are disconnected, repeat the steps that were given to you by the registration email. In order to reduce background noise, please keep all mics muted throughout the presentation. If you have any questions during the presentation, please type them in the chat box. A chat icon is located at the top right-hand side of your screen. All questions will be addressed at the conclusion of the presentation. Please note that today's program is being recorded and will be available on the ACIL website at the end of the day today. Now it is my pleasure to introduce our presenter, Carrie Organtini. Carrie is a senior scientist at Waters Corporation and has been with the company for 5 years. She received her PhD from Penn State University in 2015, studying the occurrence of dioxins and furans in fire debris and their implications to first responder health. At Waters, Carrie is part of the Food and Environmental Applications team. During her career, Carrie has developed applications using both LC and GC techniques for a variety of applications, ranging from pesticides to persistent organic pollutants. She is currently the scientific lead for developing PFAS applications at Waters. Assisting Carrie and facilitating the Q&A portion of our presentation is Jennifer Lewis. Jennifer is a senior marketing development manager with Waters Corporation, focusing on the environmental market. She supports Waters' business development teams in the Americas regions, bringing over 30 years of experience in the environmental industry to assist with customers' challenges and needs. She has a bachelor's degree in chemistry and an extensive background in GC and LC applications. Ladies and gentlemen, please welcome Carrie Organtini.
Great, thank you so much for the introduction. Yeah, and thanks for joining us today. I'm just going to turn my camera off so it's not very distracting. And yeah, I'm just going to take you through a lot of the PFAS work and applications that we've been working on at Waters throughout the last, I think it's been 4 years. So let me get that to advance. There we go. So I'm sure probably everyone, if or not, or most of you are familiar with what PFAS are, but if you're new to this topic, here's a really quick overview of what they are and why they're important class of compounds to monitor in the environment and kind of beyond, which we'll see today. PFAS and PFOA are probably the two most infamous ones, as they were the first to really the public became aware of these two first, as they're used to create Teflon coatings on Teflon frying pans and stuff like that. And because they're stable and persistent, again, they're very important for us to learn about and to monitor, and they do unfortunately have implied health effects. So as we go into looking how to monitor and find these compounds in the world around us, usually we lean towards looking at what regulations and guidelines might be out there. So currently, as of this webcast, the only really high-level regulations or guidelines that are in effect currently are for drinking water. So the US EPA currently is working diligently on creating an official regulation for PFAS through their implementation of the PFAS action plan that was kind of revigorated this year under the Biden administration. But currently, what we have to work with from the EPA is a advisory limit of 70 nanograms per liter of total PFAS and PFOA, and this is through the Safe Drinking Water Act. At the beginning of this year, Europe actually began enforcing regulations for PFAS through their drinking water directive. And per their regulations, they're looking at a sum of 20 individual PFAS, and they've set the limit of that sum to 0.1 micrograms per liter, which translates to 100 nanograms per liter, which is around a similar total to what the EPA has, but they're looking at a total list of 20 compounds. So if you just assign an equal amount of that concentration to each compound, they're down around 5 nanograms per liter necessary to be able to detect for each of those PFAS. But drinking water really is only the beginning of this issue. We use and discharge PFAS in a ton of ways in this world. So for example, I'm just showing a few examples here, but major sources of PFAS can come from manufacturing discharge, leaching of landfills where PFAS-laden products are being disposed of, and the discharge of biosolids from wastewater treatment. The byproducts and discharges from these sources obviously then do make their way into drinking water sources, but they also impact recreational and surface water, biosolids that are used for fertilization that are coming from the wastewater treatment, and water intended for crop irrigation. Again, this is really just scratching the surface. But then what happens when the PFAS make their way into these parts of the environment? They eventually make their way into our food chain and inevitably into us. So again, this is really a limited review of the pathway of PFAS that they take into the human body, and it's far more complicated than even these additional pathways that I've added here. So with that being said, I will be taking you on a journey of the analytical methods that help us make our way through this pathway of PFAS. So we're going to start our journey with environmental samples, because that's where we started when we started looking at PFAS at waters. And one of the biggest challenges of PFAS analysis, I'd like to acknowledge straightforward is upfront, is really where do you start? Because there's estimated 4,000 to 6,000 PFAS compounds that have been known to have been produced at one point in time that could have been exposed into the environment. They're all similar in the fact that they contain a carbon-fluorine alkyl chain, but within each group or subgroup of PFAS, they have different functional head groups that you can see in just a few examples of different types of PFAS. And that's the chain length as well as the functional head group changes is what it varies the chemistry of each PFAS compound. So we chose to start with a targeted approach to PFAS using tandem quadrupole mass spectrometry. And this is kind of the tried and true accepted way for PFAS analysis, and it's a really great technique because we can use the knowledge of how this molecule fragments in the mass spectrometer to really target selective and sensitive analyses for these compounds. So again, what methods were available? I mean, this is an ever-evolving list. When we started this work 4 years ago, a lot of these methods weren't on this list. So these are not the total picture, but probably the most commonly known and used methods for water, and I have one for soil analysis. So in total, there's 4 EPA methods. 3 of those which have come out recently within the last 2 to 3 years. And then there's a few ASTM and ISO methods that are also commonly used as well. And we've taken a look and evaluated all of but the newest EPA 1633 method. And we'll take a brief look at all of these methods. For the 1633 method, it's most similar to probably what I'm going to show you with the ISO methods, with a few additional requirements on sample cleanup, but that's fresh and new, so we don't really have we don't have the data to show for that one yet, but I'm sure we will in the future. So what you would have seen in the previous slide is that there's kind of you can break it down into 2 main approaches to environmental PFAS analysis. One is to enrich the sample and clean it up using solid phase extraction, or SPE. And that allows us to reach lower detection limits on a mid-tier or mid-sensitivity tandem quad, which I'm showing here are Xevo TQS Micro, which fits into that tier nicely. The other option, which I'm going to go through first, is to use minimal sample prep, where you just pretty much dilute and shoot the sample, which gives you higher throughput, but requires the most sensitive mass spectrometer that you can find to kind of reach down to the lower limits that everyone is looking for. So we'll be showing that on our Xevo TQ-XS. Before diving into all of that, I must mention, I'm sure all of you are aware that there are modifications that we do need to make to the LC to perform PFAS analysis. And this is because mobile phases and components of the LC that are necessary for it to function can contain PFAS contaminating materials. So we and most other vendors sell kits or columns to be able to hold up and isolate that contamination coming out of the solvent. So this column sits after this is our solvent mixer right here. So after everything's gone through the pump and is mixed and it's ready to go up out of the range of the picture here and be loaded onto the column, this is where we put this isolator column to really hold back whatever contamination is coming from this pump. And we can see on the left a huge PFOA peak in the blank sample, which shouldn't be there. But once we put this isolator column system on, we can get a clean blank where we expect PFOA to elute, and then we can see the background contamination coming off later, which no longer interferes with our analysis. All right, so yeah, I mentioned already that we're going to just jump into the direct inject approaches, excuse me, which we're following these two ASTM methods. So I'm not going to spend a ton of time talking about sample prep for all of these methods because that could take hours, and I don't think you want to be here for hours, but pretty much for these two direct inject methods, we're collecting a small amount of sample, 2 grams for soil, 5 mL for water, diluting it into our solvent, syringe filtering, and then injecting a large volume, usually 30 to 50 microliters of that onto our system. So you can get an idea of the water and the soil samples that we evaluated using this approach. And just kind of focusing in on the water, here is the results that we got from the 4 different types of water samples that we analyzed for this. And you can see, especially down around the totals bar down here, groundwater and effluent water, if we look at the 70 nanogram per liter, and just imagine that that's a total for all PFAS, which maybe isn't reasonable, but those two are within that limit. But surface water is getting close, and influent water is quite high. But the good news is at this wastewater treatment plant, they're removing most of the PFAS in that sample, which keep in mind, because we'll kind of circle around to a different water treatment plant that I've looked at for the SPE data or method. So the SPE enrichment for PFAS in water really encompasses a lot of different types of water. The 2 EPA 500 series methods are pretty well known for their drinking water methods. Excuse me. I don't know what's happening to my voice. Give me 1 second. And then we took the approach of looking at the ISO methods for drinking water and non-potable water, so everything like surface water, wastewater, stuff like that. At the time that this work was done, actually only ISO 25101 was available. It's very similar to 21675, except they expanded the list from just PFAS and PFOA to, I believe, I'm blanking now, 30 compounds maybe. And as I mentioned, EPA method 1633 kind of leans towards this approach with some more additional cleanup steps added. So just a really quick overview of the two drinking water EPA methods, if you're not familiar with them. They do have a specific requirement on the SPE cartridge that's used, as well as the list of compounds that are monitored. So for 537, that uses a styrene divinylbenzene phase, and EPA 533, which is the more recent one, uses a weak anion exchange cartridge. So unfortunately, I guess we looked at some of the tap water in the headquarters building in Milford and for waters, and found PFAS in our drinking water there. We also, while evaluating 537, looked at some bottled water, which looked a lot cleaner than the tap water. It's interesting to note because even though there's a few extra compounds detected in the 533 method because they weren't part of the list for 537, these two methods were evaluated maybe I'd say about a year apart or so. So seeing the change in total PFAS and the levels of individual compounds being detected is pretty interesting. Kind of shows the nature of PFAS contamination. So 533, I mentioned, uses the wax cartridge, and we've also used the wax cartridge for non-drinking water or EPA-based drinking water methods, which follows this very generic protocol. If you're interested in the full protocol, there's links to app notes that we can help you find, but this is sort of the overall overarching protocol. You'll see wax turn up in other methods later in the presentation, and this is kind of the skeleton that we follow, where the pH, we utilize pH adjustments to trap and elute compounds off the cartridge. And the reason why we use weak ion exchange for PFAS is because of the mixed mode retention mechanism that it has. Sorry, this image is a little blurry, but I think you can kind of still see what's going on here. So like the styrene divinylbenzene or SDVB that's used in EPA 537, we do have a reverse phase retention on this cartridge, but what enhances it is the ion exchange retention that we get from this functional group. And if you just take a look at just a very few examples of PFAS structures, you can see why having both the reverse phase retention for the nonpolar alkyl chain and then the ion exchange retention for the polar head groups is really benefits PFAS extraction. So what we did was we have some really kind collaborators that sent us some wastewater samples, and then as far as surface water and drinking water, those were collected locally. So the surface water we pulled from a 14-minute drive from our headquarters in Milford, from a pond, a little recreational pond called Hopedale Pond in the next town over. I naively thought, oh, there's really not much like industrial. This is like a community. There's a park over here. There's not much really that's going to contaminate with PFAS, right? Well, I was very wrong. If you track the source of the Hopedale Pond further up north, it does go through some pretty industrial areas. So we detected quite a lot of PFAS in that sample, which is bad for the people that use it for recreational purposes, but I guess good for our example here. So I'm just also showing that obviously with every batch of samples that we extract, we perform lab blanks and QC samples to make sure that we're not quantifying contamination, and that we can produce a blank sample. And for all 4 water samples, this is kind of a really busy slide. I've broken down by concentration category because these were all over the place. But what really was the most interesting about this set of samples was, if you look down at the bottom graph here, the green bars are influent wastewater, so non-treated water. The purple is what's being discharged as effluent water after treatment. So this is a different treatment plant than the previous wastewater we showed, and whatever process they were using at this facility was actually probably, this indicates that there were precursors that were present in that water that turned into these PFAS during the treatment process. So, and this is a phenomenon that is seen in other studies as well, which is unfortunate. So that was a whirlwind drive through our journey of environmental analysis, but one of the easiest ways, I guess, to follow the journey of PFAS is by paying attention to the media. I'm sure everyone probably turns on the news or checks their online media outlet, and there's usually, I'd say, at least once a week or more frequently, there's a PFAS article lingering around. So for a long time, PFAS was known mainly as a water contaminant, but in more recent years, attention has been shifted to other areas. And one of the first big area outside of water that I personally saw PFAS coming up in was food. There was the Chipotle disaster, I guess, where they found PFAS in the Chipotle bowls. So yeah, that's kind of the next place that we started looking into. So we started out with looking at produce, just because it's probably one of the easier matrices to work with, and the fact that we know a lot about these matrices based on pesticide analysis. We also threw milk in there. So we we picked some matrices that had high water content, were grown underground in possibly contaminated soil, in bogs with possibly contaminated water, to try and highlight different commodity classes. And then also milk was thrown in there. And what we did was we evaluated the FDA catchers method that was updated, I believe, in 2019, if I can get the years right, but time is nothing to me anymore. So I may be getting the year wrong, but yeah, so they use a catcher's approach to extract PFAS from food. And we followed that protocol, except we made a few changes. We changed up the salts a bit, which didn't change the results. We did a comparison. So these are actually the AOAC buffered salts. Removed GCB from the cleanup because we were seeing loss of longer chain compounds with GCB, and then did a dilution step, which they didn't do in that method, but overall it was kind of the same story. And we used this for both produce and milk samples. And if you're, excuse me, if you're not familiar with what catchers is, it's used frequently for pesticide extraction in food and mainly vegetables, but it's been adapted to other types of food materials. And the name comes from quick, easy, cheap, effective, rugged, safe, which is kind of tells you the whole story of catchers. So what this consists of is weighing your sample into a tube, dumping a packet of salts in, or putting your sample into the tube, putting your extraction solvent in, which is usually acetonitrile, and then putting the salts in and any added water, because we're forcing doing the salting out technique where we're forcing the analytes to want to be into the acetonitrile layer by over adding salts in there into the water phase. And then usually coupled with catchers is dispersive solid phase extraction, which pretty much is just dumping the phase from an SPE cartridge into a vial with your sample and shaking it and centrifuging and doing the cleanup that way. Before I show what we found in those samples, I also want to touch on the method for more complicated samples like meats, fish, and egg. So we did evaluate the catcher's method for this, and To expand the list of compounds to longer chain compounds, it didn't quite work out very well for those. So we went towards a extraction method using sodium hydroxide and methanol, which is it's not any more complicated, I guess, than catchers, because it's just a dump in and shake type method. And then we had to do wax SPE cleanup on these samples, which is called for in the FDA method anyway with catchers, because these are much dirtier samples than milk or produce. So fortunately, again, we just went to the supermarket and bought a bunch of meats and eggs and milk. Fortunately, we only found a few PFAS in liver and in the eggs that were evaluated. And I'm just showing some chromatograms of those actual hits there. They're showing their real peaks. Yeah, fortunately, I guess the food around here that we have available to us is pretty clean. But one thing I did want to show, since there was kind of a lack of PFAS found in those samples, is we also evaluated trueness of the methods by spiking a mix of PFAS into them and seeing how accurate of a concentration of the method would report back, and just pulling out kind of a sample from each category of samples tested. You can see that the calculated concentration of those food samples is pretty close to what we expected. Liver is a little bit higher, but liver was probably the most difficult matrix to work with. So again, another whirlwind through food analysis. Most recently, the biggest, I guess, PFAS scandal in the news has been the publication of some papers showing that PFAS can be found in cosmetic samples. So this is an ongoing this is an ongoing method that we're working on. We've only done minimal amount of work so far on sort of the easier sorts of cosmetics to extract, which are powdered foundation and eyeshadow, which just uses a quick extraction in methanol and filtration, kind of similar to the direct inject method. And we actually did detect some low levels, well, maybe not so low in of PFBA, but some low levels of PFAS in both the eyeshadow and powder foundation. And this is one of the papers that that's done a lot of really nice work on PFAS in cosmetics, if you're interested in finding out more. And then the endpoint of all of these compounds being found in these samples is human exposure. And you can sure find enough media and news articles about exposure of humans in the long run to these compounds. So we wanted to look at creating a method or evaluating a method for really looking at that endpoint exposure. So how to evaluate PFAS load in humans, looking at serum and plasma, because those are the more likely places that, well, easily accessible. You can't take people's livers and look at them while they're still alive. So easily accessible samples that we can look at where PFAS probably are going to accumulate. So again, very, very similar backbone structure of using pH to turn on and off the wax cartridge, but now we're using a 96 well plate format because we've gone from 250 milliliters of water down to 50 microliters of serum or plasma, which is quite a shock for somebody like me who's used to environmental analysis, and added a few different washed ups to help with this matrix, but overall it was a very similar approach. So what we used to evaluate this was just lots of human serum and plasma that you can purchase from vendors. So we've tested quite a few lots of serum and plasma we just kind of added recently. So I haven't done quite an in-depth study of plasma as we did with serum because the method performed the same. So we don't really know what the background and history of these samples are. They are a pool of both male and female samples from various people. But it's interesting to see the trends of what PFAS are present. A lot of them are very similar, but in different ratios. So you can see lot 1 had an overwhelming portion of PFAS, as well as lot 2, where serum was predominantly PFBA, with still like a quarter of the total PFAS being PFAS. And plasma, interestingly, these don't correlate at all to the sources of the samples. I don't know if plasma normally is lower in PFAS than serum, but certainly this one was, which I guess is good for these people where these samples came from. So yeah, it's a interesting way of kind of seeing the endpoint of environmental exposure, looking at human samples and seeing how similar and different they can be. And kind of to end our journey and our story, we've also done some work into non-targeted analysis using high-resolution mass spectrometry, specifically a quadrupole time-of-flight instrument. And this is kind of our way of being able to find the new PFAS out there, right? We can focus on a list of 30, 50, 100 compounds, but as certain PFAS are becoming not being used anymore in industry, they're being replaced by different types of PFAS. And I've highlighted probably the story that everyone's familiar with is the GenX Cape Fear story, where it required a high resolution instrument to be able to discover GenX in the Cape Fear River. And without that technology, we probably still wouldn't be aware of it. So I've kind of already gone over this slide, why high-res MS is helpful for PFAS, but if we kind of harken back to the 4,000 to 6,000 compounds that could potentially be out there, plus any of the new ones that we don't even know about, that's going to be a tedious process doing targeted analysis for all of those. And it can also potentially help with source apportionment and environmental forensics investigations into PFAS sites. Just a very quick overview. On our QTOF, we use a data independent acquisition that we call NS to the E. And if this cartoon kind of is confusing, pretty much all it really does is it's collecting high collision energy and low collision energy full scan data in parallel. So with one injection, we're getting the low energy precursor compounds as well as the fragments generated in the high energy function. So we can get a lot of information from one injection, which will help us identify new compounds. So for this analysis, we use the same samples that we evaluated for the direct inject method because we didn't want to bias what was in the sample by potentially removing anything using SPE. So one of the soil samples that we did characterize previously on a tandem quad instrument, we got this hit for this compound at 278.9705 parent mass. That wasn't in our library that we created which contained all of the compounds that we had already pre-screened for. And using some of the discovery tools in our Unify software, we were able to come up with this potential structure and formula for this compound, which obviously looks like it's fluorinated. So we went into, so from oops, I want to go back for a second. So from this piece of software, you can directly go into, because we're using outside databases like ChemSpider to do this candidate mass searching. So we did go to the hit in ChemSpider to see more about this compound, and you can see articles and different information, synonyms and stuff for this compound to see if, get a better idea if it's something that you're interested in your compound, and obviously, sorry, in your sample. And obviously we were interested in this because it was a PFAS type compound, and we're able to clearly identify it as this PFMBA compound, and then add it to our library, because now we know that compound information. We can continue to build our library based on unknowns that we found. So we did actually verify with a standard for this compound. So we're confident that that is actually a real hit in the soil sample that we obviously missed the first time around on tandem, running on a tandem quad. So I'm out of breath. I'm sure your heads are spinning, because that was a lot of information. But hopefully that gives a good overview of what we've been working on, as well as the importance of having all of these different methods in the different pathways of PFAS exposure, really from the discharge into humans. So with that, I just want to acknowledge our collaborators at the EPA and at UMass Amherst, as well as my colleagues here from Waters, who have all contributed into the story, the Waters story of PFAS over the years, and I'm very grateful for them. So I think with that, we'll probably turn the cameras back on and throw it over to Jen.
Okay, thank you so much for your presentation, Carrie. And at this point, I will turn it over to Jennifer to facilitate our Q&A. And just a reminder that there is a chat box in the top right-hand side of your screen, so you can enter in your questions there.
Well, hello, everybody, and thank you, Carrie, for going through that wealth of information and taking us on that journey from water to serum to non-targeted analysis. It was very interesting. We do have a question, and I think it's a good one to kick off with here. So the question really is for various diverse sample matrices, a lot of which you went over today. Do both the sample preparation and the instrumental analytical technique make customization a challenge to obtaining, the relevant data that you're looking for? And they went on to say, thinking of foods, oysters, cranberries versus wastewater versus AFFF and so forth. Like, how would you comment on that as you've worked on a lot of these matrices yourself in the lab?
Yeah, so I hope I'm interpreting the question the way whoever asked it meant, but as far as the overall, so we do have specific groups of commodities that are handled the same way as far as extraction, but yeah, obviously there's kind of a wealth of different extraction techniques that could be used for varying matrices. As far as the kind of analytical end of that, the same, I didn't put a slide in here, actually. I should have, on the actual LC and MS methods. So the same LC method we utilized across the board for all of these compounds. The only change that was made was based on the human samples. There were some matrix interference compound specific to human type samples that interfered with PFAS and the C6 sulfonate. So we used a different column for that analysis, but otherwise across the board we use the same analysis method on the back end, regardless of whether it's TQS micro, TQXS, or the sensitivity. I'm not sure if whoever asked the question wants to come on mic and clarify, maybe. I guess I'm not sure if I've answered your question properly.
Hi, Carrie. It's Eileen Snyder with Alpha Analytical. So thanks for doing this program. And yes, you did answer the question. Obviously, with the news cycle now, everyone's getting freaked out about PFAS everywhere. So as a laboratory that runs PFAS analysis, we have an ever expanding repertoire of procedures for what we call non-standard sample matrices. So it's kind of, what are some of the challenges that laboratories are up against? And is it kind of more on the front end preparation, or is it the front end and the back end analytical? So thank you.
I'd say, like I said, I think the back end, the analytical back end, unless there's, a matrix that is very, very different, that requires some special analysis, I'd say that the analytical end is probably gonna suit most matrices. And I didn't show the exact procedure for the wax SPE in the water samples, but it's very similar to what we adapted for both food and biofluids. So yeah, we've tried to keep things similar as possible, if we can. Obviously, catchers is the same as SPE, but yeah, just because being aware that labs like yourself are being asked to process so many different types of samples, the more similar they are, probably the easier it is going to be for our customers. So yeah. Any other questions, Jen?
Well, I was thinking, maybe playing into that, could you comment? I know in the early part of the presentation, you highlight the TQS micro aligned more with sample, SPE prep, and then the XS with more direct injection. But I know we've had customers that have asked the question, can you apply? Can they cross over and do the other types of methods? So maybe you can just comment on, can you use the instruments in different ways than you've sort of outlined at the beginning?
Yeah, I mean, it kind of all, when somebody asked me the question of what kind of instrument they should be looking at for PFAS analysis, the first two questions I ask are, what limit of detection are you looking for? Like, what do you have a requirement that you need to get to, or is, as low as you can enough, as well as what type of sample prep are you prepared to do? So certainly direct inject can be performed on a TQS micro or lower sensitivity type of instrument, but you're not going to get as low as you can on the highest sensitivity instrument. We do have a unispray source, which is different ionization than electrospray, that provides a little bit of boost of sensitivity for PFAS, where we've had customers that are utilizing a TQS micro with unispray to be able to do the shoot and dilute type method and reach the levels that they need to see. The reverse is true also. You can certainly prep samples using SPE or sample prep and run them on a high-end instrument. You'll just see even lower. So yeah, it also kind of, obviously brings into budget as well. But yeah, I guess those are the two main things that if you're in the arena of looking for purchasing an instrument to know which way to go is to really consider how low you need to reach and what sample prep you're prepared to do.
Okay, thank you.
Mhm.
I know I don't see any in the chat. Oh, maybe here's another one from Eileen. Do you forecast the expansion of the non-targeted analytical approach as a logical extension of the targeted run, similar to a GCMS library scan for ticks that's common in environmental?
Yeah, I think in general, high resolution MS, in general, environmental, not just PFAS, but environmental methods and is kind of gaining ground, and I don't think it'll ever replace the sensitivity of a tandem quad, just because of the the way a high-res system works, but it's definitely being talked about, and I do hear from quite a few customers from different commercial labs, research labs, all over the board, starting to think about looking into high resolution mass spectrometry for PFAS and other environmental projects as well, just to get a broader scope. Maybe use it as a sort of a screening step in their protocol for analyzing samples, and then see what pops up on the high resolution instrument, and then focus in on that, on the tandem, to really get down into the nitty gritty quantification. But yeah, it's definitely been a hot topic, I think, over the last few years.
And certainly we'd be interested to hear from the audience here today if there's any, challenges that you're having, or, you can share with the group, or love to hear those from you, or where's your next, future state going to be that we can maybe help you with.
What's missing? What's missing that we haven't done? I have an idea of maybe one of those areas, but
yeah.
So if I can, this is Eileen Snyder again from Alpha. Two follow-up questions. One is on more of a totals approach. I know if you look at the EPA method development website for PFAS, they're kind of indicating this will be coming soon.
yeah.
And then secondly, the air matrices, more of a sort of a stack testing or deposition versus, the volatilization. Do you have any commentary on those two topics?
Yeah, so the second one, the air testing, is the one that I think is the one I said I have an idea of one area that might come up as missing. That's at least in the so the organization that I'm in Waters, is a global organization, so we work on methods that apply to around the globe. But as far as PFAS and air, it's definitely becoming more of a commonly talked about and research topic in the US. I don't think it's quite picked up as much steam in Europe and other parts of the world, but yeah, I definitely see that as kind of the next big area of PFAS method development. And I know what the US EPA is working on some methods for that. And as far as the total fluorine, total PFAS, yeah, that's always another interesting area. I think people have, kind of going back to the other question about high resolution mass spectrometry, I think people have maybe pondered whether that could help characterize the total fluorine content or PFAS content of a sample. But I think the most common ways are, I'm blanking now. on doing the total, breaking it down into just fluorine and measuring that. That's not, I mean, that's not an area that we've spent a lot of time looking at or working in, but if it's definitely, I think in our thoughts and in the forefront of what's being discussed in the PFAS world. So yeah, I think you're spot on there. I agree with your assessment of what's coming as well. And I think as far as what's potentially coming in the future, I mean, you probably all know as much as I do or more, but I think we're going to see the FDA looking more into PFAS in food as well. And I think we need to wait for the EPA to set a limit in water for any other limits to come, but I think we're also headed that direction too. So PFAS is a great area to be in right now. Lots going on.
I was going to ask you, Carrie, I know you touched on it just a little bit, but what were some of your challenges when you were working on the serum methods? I know that was a bit different than some of the other, water and soil and food applications that you've developed.
Yeah, I mean, it was just for me personally challenging to kind of shift from things like water and soil, even like I've had past experiences in doing pesticide analysis in food into that human biofluid realm. I guess just kind of getting familiar with the type of matrix was the most challenging for me personally. I personally love the idea of sample prep, SPE, in a 96 well plate because it goes much faster. So that was an added bonus. But yeah, and also the kind of shifting gears in the whole sample size, going from massive amounts of water samples to just microliters of serum was probably the biggest adjustment. But once you get past that stage, it's pretty similar approach to anything else, because the same set of compounds, same type of chemistry, just being mindful, I guess, of different matrix interference. But that's in the food and environmental world, that's, I think we're all conditioned to really understand that, because there's such a wide variety of types of samples that we work with every day. So yeah, it was a fun learning curve.
Very good. What about, I'll wait and see if anybody else has any more questions, but another question that does come up from our customer base sometimes is, once you're using a system for PFAS and you've put this, adaption on there, the kit and all of that, I mean, is that instrument able to alternate to other applications, other methods? Can you comment on that?
Yeah, I mean, in a perfect world, my answer would be you should have a dedicated system for just PFAS, but that's not possible for a lot of customers that are doing different types of analyses, although PFAS might pick up enough that you don't have time to do anything else. But you can utilize the LC for other applications and methods. What I suggest, and obviously between doing a PFAS analysis and a different method, you would take the isolator column off just to preserve the lifetime of that column, as well as it adds a bit of back pressure to the system, so you don't want that to interfere with your other method. But then I also suggest, so one of the pieces of the kit is PEEK mobile phase tubing that you swap out the Teflon tubing that comes installed on the instrument with. I usually advise customers that are going to use it for multi-applications to dedicate 2 lines on their pump to only PFAS, and then use the other 2 lines for your other method if you can, just to, you know, make sure that whatever's going through those lines and into the pump is you're taking care to make sure that it's as PFAS free as it can be. And probably, I would also probably suggest in that case, if you're swapping methods on that instrument, to have if you're using the same analytical column, so say you're using a C18 for both of your methods, the PFAS and let's say pesticides, I would have a dedicated analytical column for PFAS analysis, just because you don't know maybe what you're injecting in the pesticide analysis may be highly contaminated with PFAS. You're just not looking for them, so you don't know. So that would kind of get rid of any accidental contamination events by swapping between the 2. But it takes, like, I'm very used to putting the kits on instruments, so it takes me maybe like 15-20 minutes to do it. Maybe someone that's not done it yet, maybe an hour. So if you need to swap between the 2 and you really want to take everything off and back on again, it's maybe an hour out of your day to do that.
Great, thank you. That was a good explanation.
I'm lucky enough to have a dedicated system, so
Yeah.
I'm lucky in that sense.
Always good to know, though, if you can have some flexibility. Yeah.
What I'm not lucky in is having a dedicated sample prep area for just PFAS. We share our prep lab with people doing all sorts of analyses and extractions, so it can get tricky when it comes to contamination.
Yeah. I know we just have a couple minutes left, so I don't know if there's any final comments or questions anyone has.
I do. It's Eileen Snyder again, if I can.
Yeah, no worries.
So I'm thinking of, you know, like contamination levels. You know, we try to kind of segregate sample types on instruments, but sometimes, you know, we receive samples that are a bit hot, unknown oftentimes to the customer. Is there a way to set up an instrument in more like a screening mode? And I'm thinking of, you know, kind of other typical organics that you might kind of do that before you set up to do your low level run.
Yeah, I've spoken to customers in the past who have gone to this sort of approach because they've had an accidental contamination from a really hot sample. And kind of the approach that they take is to utilize more of the direct inject or dilute and shoot type method to, and they dedicate an area and a system for that. So all the samples that come in that are slotted for PFAS analysis, they just take a bit of the sample out, dilute it, run it on that instrument to get an idea of, is there a huge level of PFAS in this sample? And then based upon those results, they move it to one of 2 SPE setups. So one is dedicated for those really contaminated high level samples, and the other one is kind of like for everything else that didn't have high hits in that screening phase, because that's another point in the method where really knowing what samples you're putting through can be beneficial for preventing contamination. And then they do the SPE cleanup and run it on their whatever instrument they use for the quantitative purpose. It's kind of a method of luxury, I guess, if you can have 2 systems. But even, yeah, I mean, I guess if you start out, if you're going to use the same system to do the screening, you could use a really big dilution or do a series of dilutions of that sample to see obviously start with the biggest solution and see what's going on, and get an idea of if you're seeing something, then it must be a really, really bad sample. So you could also use TOF, I guess, if you had that in your lab to do that sort of screening as well, preliminary screening.
That's a good question, a good area
Yeah.
to investigate. I know from personal experience, years back, those hot samples are not fun to get. So, well, I know we're at the top of the hour, so I appreciate everyone joining us today. I hope that you found the presentation and information Carrie presented helpful. Certainly, if you have any questions, feel free to reach out to either one of us, and we'd love to hear from you. And thank you so much for your attention today. And thank you again to the ACIL for letting us have our webinar and hosting us. We really appreciate it.
Thank you very much.